Today's seminar's title is Building Seismic Response versus Soil Depth. Building Seismic Response versus Soil Depth. In order to understand this title, we need to have some backgrounds. And over here, if we break down the contents, we could break them down into 5 items. The first thing we're going to talk about buildings rigidity versus buildings lateral sway. And the second, we're going to talk about buildings fundamental natural period versus building shapes and sizes. So the basic thing that we need to know about is the fundamental natural period. The third one would be about earthquake waves and their period length. The fourth thing we need to know about is building sizes or shapes versus earthquake waves, how buildings respond to earthquake waves. And the last one for us to observe, we have an observation about earthquake damage intensity versus soil depth. Okay, and the last thing would be the conclusions. In this slide, we could see buildings sway back and forth during an earthquake, which means all the buildings around the world, when an earthquake hits, whatever the building height is, no matter how big the building is, there is a natural response for the building toward an earthquake. So when an earthquake hits a building, the building tends to sway. We could model any building with an inverted pendulum and see how the building would behave based on the pendulum behavior. So when, as I mentioned to you, when an earthquake hits a building, then you're going to see that the building starts to sway naturally from one side to the other side. Okay? In this slide, we see buildings with different degrees of rigidity. Some of you might look at them buildings with different heights. Yeah, that is true. We want to highlight one thing that is related to probably height and other things, but we can, based on our intuition, we can classify them into rigid, less rigid, and less rigid, which makes it more flexible, less flexible, and the least flexible one out of these 3. And when an earthquake hits any of those buildings, the natural response for any of those buildings would be swaying. So any building starts to sway as a response from one side to the other side due to an earthquake force. And the speed at which it starts to sway from one side to the other side, it depends on many factors, but we oversimplify it into, like, as I mentioned to you, rigidity, degrees of rigidity or flexibility. So the rigid building, when an earthquake hits a rigid building and the rigid building start to sway laterally, it starts to sway laterally in a very rapid manner due to its rigidity. So it goes back and forth very rapidly. But when the height increases, that gives some flexibility to the building, and when an earthquake hits that building, then you're going to see that the pendulum starts, which represent the behavior of this building, starts to also sway laterally, but less rapidly than the rigid one. And for the flexible one, the tallest one, when an earthquake hits, the natural response to the earthquake would be again swaying laterally from one side to the other side, but this time at lower speed. So the speed at which the most flexible building tend to sway from one side to the other side would be at very low speed. Now, if we convert speed into time, the one that sways laterally very rapidly means it takes a very short time for it to complete a single cycle of back and forth. So the time needed for a short building or a rigid building to complete a single cycle of back and forth is really little. When it goes to a building that is more flexible and less rigid than this one, in order for this building to complete a single cycle of back and forth, okay, it takes a little bit more time for this building to complete a single cycle. And when it goes to a building that is really flexible, then you're going to see that the building tends to sway laterally very slowly. So it takes longer time to complete a single cycle of back and forth. Fundamental natural period is the time needed for a building to sway back and forth, as I've shown to you, back and forth, okay, from one side to the other side, to complete a single cycle. And that is classified or known as fundamental natural period. So it is an inherent properties of the structure and are influenced by many factors. They could be height, mass, or the materials the structure is built up with. So many other factors also we have that could influence the fundamental natural period. Okay, and if you look at the time needed for this single-story building to complete a single cycle of back and forth is 0.05 second, which means it starts when an earthquake hits this building. It starts to really sway laterally very rapidly. But when a taller building than this one, lower rise building, even though it's lower rise, but it's taller than a single-story building, when an earthquake hits it, you see the fundamental natural period is a bit longer. The time needed to complete a single cycle of back and forth is longer, is 0.4, while for the short story or the single story is 0.05, so it's longer, the time needed. And the taller the building is, the more flexible, as I've mentioned to you, then the time needed to complete a single cycle of back and forth would be longer, and that is 1 second. So the fundamental natural period increases with the flexibility, increases with the flexibility of the building. And this structure would show that it's not all the time about height to increase the fundamental natural period. You see that this is a reinforced concrete chimney of course less height than the 15-story building, but at the time needed for this building, due to maybe it's hollow or whatever the reason is, you see that the time needed for the structure to complete a single cycle of back and forth is 2 seconds. It's really long. That means that makes it too flexible. Okay. And then based on your intuition, when you see a large concrete dam, okay, you definitely know that the structure is not flexible. So, and that shows the structure isn't that flexible. 0.85 seconds, the natural period of the fundamental natural period of this structure, which means it needs that much of time in order to complete one cycle of back and forth when an earthquake hit this structure. And when you look at a bridge that is flexible, like this suspension bridge, when an earthquake hits this bridge, it takes 6 seconds for the bridge to sway laterally and complete one cycle. So it really gets really long for the structure. It takes really long time for it to complete a single cycle compared to a structure that is rigid. Here we have 0.8 seconds to complete a single cycle of back and forth, and over here with this structure we have 6 seconds, okay, to complete a single cycle of back and forth when an earthquake hit both of them. Earthquake waves. We've talked about the most important characteristic of the so-called fundamental natural period of the buildings. Now we need to know about earthquake forces. Of course, an earthquake force contains a bunch of waves. Earthquake contains a mixture of many sinusoidal waves. That means an earthquake force is represented by a bunch of waves, and those waves of different frequencies. They are ranging from short to long period. And again, we need to understand what period is meant. And waves is the same thing. Period is the time needed for an earthquake wave to complete one cycle of motion. If you look at this graph, you understand that this is a wave. Okay, this is one cycle of motion. The wave is repetitive. That means it repeats itself all the time. So in order for the wave to complete one cycle of this shape, it takes that much of time, and this time is called period. And we classify those waves based on the time needed to complete this shape. So the time for the wave to complete this one cycle of motion is that much, which makes it short, because if you compare it to this wave that is long, the time needed to complete this wave, which is also repetitive, and it's a sinusoidal wave, it looks like a sinusoidal shape, okay, then the time needed is long. And if you compare this to that, then you will know that this is the short wave and this is the long one, and the one in between is neither short nor long. Okay, so we have earthquake ground motion, or strong earthquake ground motion, transmitted by waves of different periods. That means we have a bunch of waves traveling through the earth in order to create a seismic motion. Okay. Now we've known about buildings, inherent properties. We've known about earthquake waves in terms of period length. Okay, some of them are short, some of them are long, and some others they could be in between, and so forth. We need to understand how those buildings of different inherent properties they behave versus different earthquake waves. In a typical city, we have different types of buildings in terms of sizes and shapes, and that's what makes the building rigid or flexible. And that means when you have a rigid building, you, based on your intuition, you would know that the building is its natural, its fundamental natural period is short. When you see a tall building or a thin or slender building, you would know that that building or structure is flexible, and the fundamental natural period would be long. So different sizes and shapes are categorized by the fundamental natural period, which means we have different fundamental natural periods based on probably sizes and shapes and other factors as well. If the ground is shaken back and forth by earthquake waves of short period, if we assume that the ground is shaken by an earthquake force, and that force has one type of waves, and those waves were of short period, then you're going to see only buildings of short fundamental natural period, which means rigid buildings, they will have large response to that earthquake force. Okay, this is an assumption. If we assume that there will be an earthquake of single type of waves, okay, then the building that would have high response to that wave, to those waves, would be the building of the same period, which means short period with short period. In 1967, an earthquake hit the capital city of Venezuela, Caracas City. We observed that response of buildings versus soil thickness underneath the buildings. Okay, now we have observed in this mishap that took place in 1967 in Caracas City, the capital city of Venezuela, which means South America. Okay, a 3 to 5 story building, which is it could be considered as a low-rise building or medium-rise building. Okay, we have seen that those buildings had higher damage intensity in areas where the soil thickness were of 40 to 60 meters, yet minimal damages in areas with thicker soil, which means 3 to 5 story buildings experience severe damages in places or locations where we had a thin soil cover, okay, while minimal of damages or no damages experienced by buildings of the same height, but in areas where the soil thickness were thicker. Okay. For other types of buildings, 10 to 14 story building, we could classify them as a bit high rise building. They are a little bit high, okay. Those buildings, they experience severe damages in places where thick soil cover. That means where those buildings were standing on thick soil cover, they experienced severe damages. That means damage intensity was high in those places, while a number of buildings of the same height in other places where the soil thickness was thin, they experienced little of damages, or less damages, or minimal damages, and probably no damages at all. So in order to visualize these two things, I will show you this graph. This is the damage intensity versus soil thickness, which means damage intensity versus the depth of the soil underneath the building. Underneath the building we have soil, so the depth of the soil underneath the building. If you look at the damage intensity versus soil thickness for those buildings of 3 to 5 story buildings, okay, buildings of the same height, we see building of the same height, when the soil thickness was low, they experienced severe damages, while the buildings of the same height in locations where the depth of soil was really high, they did not experience damages, or the damages were minimal. And that is what we can see from the damage intensity. Over here, the thickness is thick for the soil cover, and you see the buildings of this height experiencing minimal amount of damages, while the same, other buildings of the same height in places where the soil thickness were thin, they experience extreme damages or severe damages. And the same thing goes to buildings of higher height, like 10 to 14 story buildings. They experience severe damages when they were in locations where the soil depth was really deep or high, okay? While buildings of the same height in other locations where the soil thickness was low, they experienced less damages, okay? The intensity, or the damage intensity, was very much less compared to other buildings of the same height but in other locations. And the force was the same force. An earthquake force hit the whole region, the Caracas region, the Caracas city in 1967. The same earthquake force hit the place. But you see that the buildings behave differently, or experience different level of damages for short story buildings and tall buildings based on their locations. And we can conclude from that those buildings who were short and placed in areas where the soil thickness was little, okay, not deep. As I've mentioned to you, earthquake forces, there are a bunch of waves. So we have long and short waves. And as a principle, we know that short buildings respond or have higher response to waves of short period. So that means the only waves that reach the buildings of this height in this region, the waves, they were of short period in order for the building to experience severe damages. So that means the soil did dissipate the waves of long period, while in other places where the soil thickness was high, okay, the damages were not severe, or they were minimal, because the soil did filter the short waves for the short building story. So when the short waves are filtered, only long waves are reaching the building wouldn't respond to long period waves, because the building is of short period length. And the same thing is applied to the high-rise building. When they were located, in an area where the soil thickness was high, so they experienced severe damages because the only waves that did reach those buildings were of high period. Okay, high period. That means the soil did filter the short and did not filter the long period ones. Okay, the same another bunch of buildings of the same height, they were located in places where the soil thickness was really thin. It didn't experience that much of damages because the soil did filter the long waves and did let the building to get exposed to only short waves. And short waves doesn't affect tall buildings, because tall buildings, their fundamental natural period is long, as I've mentioned to you. So that is based on this graph, we could conclude that soil as a medium, it works as a medium and it filters or dissipates waves. And when the thickness is thick, it dissipates short waves. When the thickness is low or not or thin, then it starts to dissipate long waves and let the short waves to reach the building. That's why buildings of short period, and those are the short buildings, they get excited by the short waves and eventually experience severe damages, while the tall buildings, they get excited by long waves because the medium doesn't filter or dissipate the long waves and let the long waves to reach the building while it filters the short waves, so they would experience severe damages in area where the soil thickness is thick. That would be the end of my seminar, and thank you very much.